Hi everyone, welcome to round 5 of the same video. I am going to try super hard and maybe this is lucky number 5. Let's see if we can get the sparkle back in my sparkle pen. I'm having a hard time getting these videos to save. Oh, sorry about that. I was trying to draw a smiley face and it wasn't really working. Let's try to get, oh, there we go. I'm at a neutral smiley face with my sparkle pen. All right, let's start Unit 3, and I'm really excited about Unit 3 because I think if you were to ask anyone in chemistry what's one of the most important things that we learn in Gen Chem 1, they're going to answer the mole every single time. And if you were to ask students what's the one thing you hate from Gen Chem, they're going to answer mole every single time. So let's take this first video. Let's go through the history of the mole. We've already looked at the history of the atom a little bit. I want to add to that the history of the mole. And then I want to take my time and really define the mole, why we give a crap, and then do a couple problems. And my goal is by the time you finish this first series of videos that you're able to do the first homework set. So let's start with a nice general history. This is going to be fun. Let's go back to 1805 Dalton. And I'm gonna post this Word document online for you also on Blackboard, because you'll notice everything we talk about, I'm going to have a nice little tab for you, a nice little web link. So if you want to know more, you can check that out. But whatever I test you on would be on this document. I don't want it to feel overwhelming. So back in the 1800s, 1805, this is way before we even knew what an atom looked like, Dalton had this crazy idea. You know, they're studying chemistry by now for about 150 years since the switch of alchemy to chemistry. We learned that was in the 1600s. So he had this idea, out of all this studies, so far the element that they've come up with that's the smallest and they've observed so far has been hydrogen. And so he had this idea, well, hang on a second, if we're going to start to look at all of, you know, what's around us, what's in the world around us, and matter and what is made of, we've got to really try to get to the smallest unit, smallest thing, smallest particle, smallest element, where we need a place to start. How small can you go and still have the same properties and everything in that substance, whatever it is. So he wanted to start first with hydrogen. You know, back in the day, this was the smallest element that they could get their hands on, and it's still so far true today. So he had an idea that just stood the test of time. Hey, let's just assign hydrogen 1. It's the smallest thing we know of. Let's get small. Let's see how small we can get. Let's start with hydrogen. Let's assign it 1. And then he had some 5 general philosophies that are pretty impressive since it's been over 200 years and they have all held true. And that is that the first one, all matter is made up of atoms. Well, that's pretty cool. We still know this now, even though we've been studying our atoms for a couple hundred years. He had this idea of, well, if we can take whatever substance we're studying and get down to those elements and take that element and get to a place where you just can't divide it anymore. If you do, you don't have the same properties or mass or anything from that substance. And that was his idea of an atom. So those atoms are the smallest you can get to. You can't divide them. And that atom is the smallest piece of that element that still has its same properties. And then he got a little deep with reactions and said, okay, well then what are all these substances around us? Well, they're just a combination of different atoms. Atoms are still our smallest piece of every element. And these are just a combination of those. And then, but what happens when you have a reaction? Well, reactions are literally just a rearrangement of those atoms. So all 5 of these ideas were pretty revolutionary a couple hundred years ago, and they've all kind of stood the test of time. It was a good place to start in the 1800s, great way to start thinking about things. And so come in about 6 years later, and it was actually an Italian attorney named Avogadro that kind of took this idea and ran with it a little bit. Turns out he was fascinated by the gas laws. My handwriting's terrible because my pen is not working right now, so I'll get back to my sparkle pen, I promise. Hopefully it just needs to be charged. So he had this idea, was fascinated by the gas laws, and I better do a little labeling here on my slightly inappropriate drawing. So I want us to picture these as balloons. All right, so if you're fascinated by the gas laws and you like to party, I mean, what do those two things have in common? Balloons. So why does he care about balloons? Well, that's how you contain your gases. And so one of the things he thought about, which seems so intuitive, but it's actually fairly complex, is what actually determines the size and the shape of that balloon. I mean, have you ever thought about it? When you blow up a balloon, why do you get that shape and that size? Well, it turns out that it is all these little molecules, these little gas molecules in there, and they are smacking the side of that container. And that kinetic motion is what's giving you that pressure that's inside of there and giving you that size and that shape of that balloon. And then, of course, you have a competition of your little molecules out in the atmosphere, and that's what's giving you that size and that shape. Okay, so let's take this one step further. This is awesome. What if you love your gas laws, you love your parties, but you're also phenomenally type A? So what if you have in your mind, well, yeah, anybody can blow up a balloon, but I want a balloon that is exactly the same size. Literally, I want these two balloons to equal. Okay, well, now it gets a little trickier, but taking what we just learned in this balloon, how would you make this balloon the exact same size? Well, if what's giving you the size and the shape are these little molecules smacking the inside of the container, literally those little gas molecules smacking the side, well, in order to have the exact same size and shape, don't you need the same number of gas molecules? Yes. So you're thinking, well, that's totally logical. That makes sense, right? So why was it then that it actually took another 100 years for people to look at Avogadro's ideas and give him credit and actually accept those ideas? And in fact, it's been 200 years of the definition of this hypothesis and principle. It's been really fascinating. So here's the caveat to that. Okay, so I think this part makes sense. You need the same number of gas molecules in each balloon in order to give you the same size. But here's the tricky part. You can have different gases. So the actual type of gas didn't matter. Okay, now we're getting trippy. So let's start to picture. What if you have hydrogen in this balloon and you have carbon dioxide in this balloon? Okay, you could still have them be the same shape and the same size, but what's going to be different? They are going to weigh different. Okay, this is one of the hardest things in chemistry. This whole concept, it was so hard to fathom because weighing something is really easy to do. We can do this in the lab, very easy. But actually figuring out how many gas molecules are in those balloons, now that's tricky because you can't see them. So this is a really important idea. Those two balloons can have totally different weights. That hydrogen balloon, the second you let go of that, it is going to float off into the atmosphere and occasionally end up in the ocean and kill a turtle. You know, you got to be careful with that. That CO2 balloon, you let go of that thing and it's actually just going to sink and sit by your feet, maybe roll along the grass. Two totally different gas molecules in those balloons, but yet if their size and shape are the same, they have the same number of gas particles. So this was actually Avogadro's hypothesis and his theory, and it really wasn't accepted for about 100 years. It was pretty sad. It wasn't accepted until after he died. And if you've already had some chemistry and you know Avogadro's number, he actually didn't come up with Avogadro's number. He came up with this general idea. So let's fast forward just a little bit. And here's another little link on there. So let's get to 1860s. All right, we're fast forwarding about 50 years. Cannizzaro took that idea of Avogadro's hypothesis and he kind of gave some credence to it and said, hey, hang on a second, I'm studying oxygen gas and I'd like to come up with an idea for atomic weight. How am I going to do that? So he looked at Avogadro's hypothesis, started giving some credit there. It wasn't until the 1890s that somebody then, a German chemist, actually coined the term mole, and it's German for a molecule, but he actually used that term mole almost 100 years later for that idea of what Avogadro was talking about. And then fast forward even a little bit more, the first person to actually use that idea and want to count molecules in gas laws was a French physicist and chemist, Jean-Baptiste Perrin. And in 1909, he used Avogadro's ideas and used them in his gas laws. And he gave credit to that idea to Avogadro. So this was almost a solid 100 years later. And I put a little link there for you on that one. And then right around that same time, literally within that same year, two chemists and physicists we've already heard of, J.J. Thomson and Michael Faraday, 1910s. They were taking that idea, remember, studying the electron, trying to figure out the electron. We've got the Millikan oil drop experiment. We've got J.J. Thomson's cathode ray tube. We've got Michael Faraday, who was working under Humphrey Davy at the time, who was doing what? Remember, he was addicted to nitrous, so he was taking things like table salt and zapping them with electricity and then inhaling whatever they made because of his addiction. Well, Michael Faraday was then taking that and putting a number on it. And when you hit Gen Chem 2, you're going to hit that number. It's literally the Faraday constant. He was trying to get to a mole of electrons. He was trying to correlate how much current it took to make how much gas or how much decomposition in those compounds. And he took the Millikan oil drop experiment and took that charge on an electron. He came up with his mole of electrons. And this is the first time we start to see an actual number for Avogadro. And that's where that 6.02 times 10 to the 23rd came from. It came from those studies. Now, this idea was pretty revolutionary. It ended up in college textbooks by the 1930s and then in high school textbooks by the 1950s. Isn't that incredible? Take for granted that we know these things and they end up in our class right away. And it took an awful long time for that to happen. By the 1960s, there was an actual definition. Oop, wrong pen, y'all, wrong pen. Actual definition for a mole in the 1960s. And this part was pretty fascinating. So now we're a solid 150 years later, and now there's a definition. I am going to get deeper into that definition in just a little bit. We're going to take that definition and do some math with it and look at it. Let's finish our history so we can get to the good stuff. All right, so then 1971, can you believe that? Not only was there disco, but they also made the mole an official unit. Now, what I find just totally fascinating by all of this is that it wasn't until 1980 that the mole was officially defined and called a unit. Now, of course, I wasn't born then. Maybe some of you were. Maybe your parents were born then. But it's fascinating. This didn't happen 200 years ago, and then it's just been known ever since. This has been evolving for a couple hundred years. 1980 is when the mole was actually defined. Since 1980, what's been happening is that Avogadro's number itself has been calculated many ways over. Even though the general definition most people think of is carbon, that's actually not the definition anymore. And they don't actually calculate from carbon, Avogadro's number. At least in my generation, that has come from silicon. And they will take exactly 28 grams of silicon, use X-ray crystallography. And what are they doing? They are measuring the space between silicon atoms in that cube. And then once they measure that space, they can then calculate. Boy, that's awful writing. It's almost like we're back in lecture. Once they measure that, then they can calculate what that had to be. And so in the last 200 years of just trying to define the mole, it's only been in the last 100 years or so that they've been trying to calculate as best they can that Avogadro's number. To date, as of about 2 years ago, from what I've seen, we are up to 10 sig figs in how Avogadro's number is calculated. And then believe it or not, just past November, the whole definition of a mole was redefined. And so we'll take both of these definitions and we'll do something with them. Let's actually get to my next favorite section. That'll be our next video. And that section is the why do we give a crap section. So let me see if this video recorded. Let me post it and then let me get on to the next